Hey guys, today we're going to be looking at imaginary numbers, and imaginary numbers are kind of nice in that you can now factor a lot more things, and you're able to simplify a lot more things than you were before. So today we're just going to be looking at some of the basics, and then we're going to be moving into some of the harder examples. So for the basics, these are just two things you're going to have to memorize, so the I and the I squared. I is equal to root negative 1, so not that hard to think about, but basically imaginary numbers give us ways to simplify things we weren't able to before. So if we before had negative root 3, we also said this is equal to no solution or not possible. But now with imaginary numbers, we're able to say that this is equal to root negative 1 times root 3. And because I is equal to root negative 1, we can also say that this is equal to I root 3. So that's kind of nice, and we'll be looking at that later in the video and how that helps us. So then I squared is going to equal negative 1. So I think this is also something that you have to memorize. But this is also something that's pretty easy to memorize just because you're going to be using it a lot, and the I squared makes it really nice to simplify a lot of things. So as you'll see later, we'll be able to simplify a lot of things using I squared and just making that negative 1. So then I cubed. This is something that sometimes people have a harder time remembering, is I cubed negative I or 1 because I to the fourth is 1. So a way that I've come to remember this is kind of by proving it. So you can also say that I cubed is equal to I squared times I, and then the powers create I cubed. And we know that I squared is equal to negative 1, and if we multiply that by I, which is just I, we get that equals negative I. So that's just how I like to remember it. And then for I to the fourth, a similar thing that you can do for that is there are actually two ways to prove this. So I squared times I squared equals negative 1 times negative 1, which just equals 1. Or we can do this a different way. We can do it I cubed times I is equal to negative I times I, which is equal to negative I squared, which is also equal to negative 1, because I squared is negative 1, right? And so then this equals 1. So either way, we can see that I to the fourth is equal to 1. So these are our four things. I would definitely write those down in your paper as reference points, and if the last two things don't make sense to you, you can always just remember them. It's not really that hard. It's only four things. Okay, so now we're just going to be looking at some examples and applying the things that we just learned. So this is the first example on your sheet, and if we multiply it out, we get that this is equal to negative 30 I squared, because we basically want to treat I like a variable. So negative 30 I squared. Now, the nice thing about this is that negative 30 is actually equal to negative 1, as we learned in our past basics examples. So this is also equal to negative 30 times negative 1, which is just equal to 30. So that's a nice way to apply this. Now we're going to move on to some examples that show us how we can simplify I. So all powers of I can be reduced to either I squared, I to the third, or I to the fourth. So we don't really have to worry about any of these terms up here because we're actually going to reduce those down. So in my opinion, the easiest way to do this is to find out how far away it is from 4, which sounds kind of confusing, but there are 4 options for I. So if we look at how far away it is from the 4 options, then we can see which one it is. So I'll explain this by showing you kind of how I think about it. So 31 divided by 4 is also equal to 7 remainder 3. And that's because 28 divided by 4 is 7, and then you have 3 left. So then if you look at this remainder portion, that's what goes into the exponent part. So this is also equal to I cubed, because we have a remainder of 3, which is also equal to negative I. Now if you look at I to the 74th, 74 over 4 is also equal to 18 remainder 2. And that's because 72 divided by 4 is 18. And then that's a remainder of 2 because it's 74. And so if you look at this remainder, this is what goes up in our I. So we know that this is I squared, which is also equal to negative 1. Sorry, I just realized I'm going out of order on your sheet. Okay, and then I to the 25th, this is 25 over 4, which is also equal to 6 remainder 1, because 24 divided by 4 is 6, with a remainder of 1. And then, looking at the remainder, we can just get that this is I to the power of 1, which is also equal to I. And then looking at our last example, we have that this is 68 over 4, which is just going to equal 17 remainder 0. Now, the important thing to remember here is that when we have a remainder of 0, this is also equal to 4, because we're looking at it in terms of how far away it is from 4. So if it's 0 away from 4, that means that it's going to be a power of 4, right? So if it's a 0, then this just becomes I to the 4th, which also equals 1. So when you look at these big numbers in the exponent, you always want to remember to look how far away it is from 4, and then you can simplify it down and reduce it to a smaller power of I, which we just reviewed and we know. Okay, so now we're going to be looking at how to get radicals out of the denominator by pulling out imaginary numbers. So in the last unit that you guys worked on, you learned that you can't have a radical in the denominator. So if we split this up, we get root 5 over root negative 3. So we definitely want to pull this root negative 3 out of the denominator. But another important thing to know is that we don't really want to have imaginary numbers in the denominator either. We want to keep those in the numerator. So our goal for this is going to be to pull both of those out. So we can simplify this further to become root 5 over I root 3. Because remember, if there's a negative inside of the radical, we can just pull that out and make it I. So now what we want to do is we want to take this root 5 over I root 3, and we want to multiply it by I root 3 over I root 3. And this is because we want the i's to become negative 1. And so the easiest way to do that is just to multiply by I. So those will become negative 1, and then the root 3's are going to cancel out like we just showed in the last unit. So this is also going to equal I root 15 over I squared times 3. Now what we just showed is that I squared is also equal to negative 1. So we're going to make this I root 15 over negative 1 times 3, which also just equals negative I root 15 over 3. So that's kind of nice. We can easily simplify that, and we can still solve it even though there is a negative inside the radical. Okay, now we're going to look at how to simplify something that looks like this, and just by distributing the exponents through and combining all those terms. So negative 2 to the 3rd is just negative 8, and then I to the 12th to the power of 3, remember that's multiplication, so that just becomes I to the 36th, times 4 squared is 16, I to the 7th squared is I to the 14th, so this is also going to equal negative 128, and then this is going to be I to the 50th, and so now we need to simplify it down to a smaller power of I so we can actually simplify this. So we know that I to the 50th can be written as I squared, I to the 3rd, or I to the 4th. So let's use the trick that we just used. So 50 over 4 is going to equal 12, because 48 divided by 4 is 12, with a remainder of 2. So I to the 50 is also going to be I squared. And remember, this is really nice because this also equals negative 1. So this means this equals 128 times negative 1, which also equals just 128. So to simplify that whole thing, which looks so complicated, it just becomes 128. And so that's what's really nice about imaginary numbers, is that it's really easy to simplify them, and it usually ends up being a lot less terms than with like variables. Okay, now we're going to look at foiling with imaginary numbers. So when foiling, you should always end up with at most two terms. So you're going to have A plus A of I, A plus B of I. And so these are going to be your true terms. You're just going to have a constant, and then you're going to have something with an I on the end. Or you're just going to have an I, so just B of I, or you can just have an A. So obviously it's a lot simpler than foiling with variables where you're going to have 3 terms, and I'll show you why in a minute. So if we factor this through just regular foiling, we get 10 I squared plus 15I minus 14I minus 21. And then if we start combining these terms, we get 10 times, and then I squared is also equal to negative 1. So 10 times negative 1 plus I minus 21. And then if we simplify that all together, we get I minus 31. So obviously very simple. You just have your b of I, so this is just 1 times I, minus your a, which is just 31. So pretty simple, and we're going to move on to something that is just with i's. So as we looked at in the past, sometimes when you have a difference of squares, you can end up getting something that's less than 3 terms. So this might not look like a difference of squares, but this actually is a difference of squares in kind of a weird way because imaginary numbers work a little differently. So if you get the time to look into how to create one of these, it's kind of cool actually. So if we start factoring it through, we get 25 root negative 9 minus 5 root 3 minus 5I root negative 3 plus I. So now if we start simplifying this, you can get 25I, because you can pull out a negative out of the negative 9, times 3 for simplifying the root 9, minus 5 root 3 minus 5I squared, because we have a negative 3. So we're pulling out an I from there, root 3 plus I. Then if we simplify this again, we can get 75I minus 5 root 3, and now this I squared here turns into a negative 1, so we get negative 5 times negative 1 root 3 plus I, and then this can become 75I minus 5 root 3 plus 5 root 3 plus I. And now you can kind of see how this is turning into a difference of squares, so then these two middle terms are just going to cancel out, and then we can combine these n terms, and then we just get 76I. So obviously very simple, and that's kind of what imaginary numbers allows us to do, which is nice. Okay, now we're going to look at solving for both x and y using equations with imaginary numbers, but first I think it's important to look at why this is going to work. So you are going to need to know this for your test. There's a question with graphing on it, so I would definitely pay attention to this section. So when you're using imaginary numbers, you're not on a real plane because imaginary numbers can't be considered the real plane. You're on what's called a complex plane. So when you have complex numbers, your format is a plus b of I. So this graph here is going to show you how the complex plane works. So you're going to have your real axis, which is also your A. So your A is going to be your real axis. And then you have an I axis, so an imaginary axis. And that's what your B coefficient is going to refer to. So if we just pick a random point, let's say right here. And let's say that on the real axis, x is at 3. And then on the imaginary axis, I is at 2. Then if we use this point, we can know that this point is also at 3 plus 2I. So basically we have 3 in the real axis plus 2 on the imaginary axis. So that's kind of what the complex plane is going to show you. So you can't really separate them or anything. So when you're solving, you're just going to solve for whatever axis it's on. So that might seem a little confusing now, but hopefully that will clear up a little bit in the next section. And basically all that you need to know is that, we'll look at one more point. Let's say that you have a point like right here, and this is at 2, and this is at 4. Then your point is going to be 2 plus 4I. So that's kind of what you need to know about that, and yeah. Okay, so now we're going to be working with actually solving for both x and y using equations with the imaginary axis. So, like I said, you want to solve for each term in the correct plane. So first, we need to figure out which is the correct plane. So simplifying this equation, we get, because there's an I squared here, negative 4x minus 6yi equals negative 2 plus 9i. So here's where we split them up. We want to split up the i's, and we want to solve for y in the imaginary axis, and then we want to solve for the x in the real axis. So we literally can just split this up. So you can make it negative 4x equals negative 2 negative 6y equals 9. So notice how we're not carrying the imaginary numbers over, because I guess technically they would divide out, but you're also just solving in a different axis. So you don't explicitly need to say, oh, this is in the I-axis, because you know that you're in a different kind of plane. So now if we solve for each of these, you get that x equals 2 and y equals negative 3/2, which if you plug it back in, that is correct. So, x doesn't equal 2. X equals 1/2. X equals 1/2, y equals negative 3/2. Yeah, so plug those in, those are correct. Now we're going to work with a little more complicated example, and this is going to be with systems. So if we're looking at this example, we're just going to do the same thing we did up last time. So we're going to split it up using the imaginary axis and the real axis. So this really makes these a lot easier. So now if we split it up, we get x minus 3y equals negative 3. And then, remember, for the next term, we take out the I, so we just get 2x plus 6y equals negative 2. So we're not worrying about the i's, and now we can actually solve the system of equations. So we're just going to multiply this up by 2. If we subtract, we get negative 12y equals negative 4, y equals 1/3, and then just like a regular system, we're just going to plug this back in. So 2x plus 6 times 1/3 equals negative 2. 2x plus 2 equals negative 2. 2x equals negative 4. X equals negative 2. So you can see that if you plug these both back in, they both do work. So that's kind of how you solve for those. So obviously not that hard. You just have to know that, the i's go together and the reals go together. Yeah, so I hope this was helpful. And imaginary numbers, I think the key is just to remember what I squared, I to the third, and I to the fourth is, and everything else I think you can figure it out from there.